Hi, I'm Mike Puchowicz. I'm a lead sports medicine physician at Arizona State University. Presenting this study I call Boosting with Bayes. Anti-doping classification is improved by transverse monitoring of the athlete network. I don't have any disclosures, no conflicts of interests. So diving into it. So my motivating question for this, this is the question. So if athlete doping rarely happens in isolation, why do we treat testing that way? So I kind of drew out this little figure kind of to just visualize it. And if we think about doping, there's a lot of people involved in it. There's athletes, there's trainers, doctors, coaches, there's other people. And it happens within networks with different connections between people. And within networks, there's different levels of tolerance for doping. So some people may be totally opposed to doping. Some people might instigate doping and actually bring the doping into the group. And then other people might be just merely tolerant, and other people may be reactive, where if they see a lot of doping, maybe they participate. If they don't see a lot of doping, they don't participate. And there's a lot of information to leverage here. If we looked transversely across that network, there's a lot of information that we could use to boost our results, theoretically. But we don't. When we test an athlete, so for example, athlete biological passport, we determine either they have an adverse finding or they don't. And if they do, we call them, declare that they've doped and punish them harshly. And we hope that if we punish them harshly enough, that maybe that has some kind of deterrent effect on the other athletes. But we don't know if they're in the middle of a doping network or not. We're just punishing them harshly. Also, when we think about thresholds for like an EPO test or things like that, we're not adjusting that threshold based on other information. We're not looking transversely and taking other information and adjusting that threshold. And the point of my study is to say, we can do that. And that improves the testing, that improves the predictive value. And so the way I wanted to show that this can be done is I set up this big simulation study. Simulation is partially for convenience, partially to get high numbers of data, but also because we can control the scenarios that we want to look at. And I did want to make it real world. So what I did is I simulated 5 data sets, 10,000 individuals in a data set, plus 10 member networks for each of the individuals. And I simulated this in R. And I set background prevalence according to Dahan, and they found, different prevalence, 10, 20, 30, 40, 50%. And so I chose this range, and so the 5 data sets are representing each of these different prevalences. So one group with 10%, 20%, etc. And then, the individual is then assigned randomly to either doping or not doping based on that prevalence. And then where I take it a step further, where I go further then, is to then look at that network also and say, okay, now the network also has a doping prevalence. And I rate that or give it a number from 0 to 1. So 0 meaning there's no prevalence, 1 meaning everybody in the group is involved in doping. And so that's how I created the data set. Now I wanted to test it using something that's also kind of real world, and in this case this is an emerging technology, ocular motor deception technology from Cook 2012, and we're running a validation on this. But it's a goodish test, so it's 85% sensitive, 85% specific, and it's actually looking for deception, which is kind of interesting, but it's goodish. Like, it's not great, you're not 99.9% specific, and so I wanted to compare how that's going to work on this data set versus if we boost it statistically. And so I used Bayesian statistics here because we're already doing this. There's good precedence for this in athlete biological passport. The thing I'm doing differently, though, is I'm taking advantage of the way Bayesian statistics work. So with Bayesian statistics, you start with a prior probability, and then you go and add evidence, which is your test, and then you have your posterior probability, which is your test result. That's what you actually use to determine something. And in this case, what I'm saying is our prior probability, I'm not just going to go based on just general prevalence or a coin flip that we don't know, 50%. I'm going to say that athlete's network informs their prior probability. So if they're in a network with high probability of doping, then their prior probability is much higher. If the prior probability is low, their prior probability is much lower. And so now we can incorporate that into our Bayesian equation here, and you can see how that network posterior probability is incorporated into that equation. And then I took the 85% sensitivity and specificity, from our test. And so we're combining this prior probability, this data we have from the network, with the test result. And now we're getting a posterior probability. And I'm going to show you that this posterior probability has now been boosted and much better. To classify something, I used a cut point of 0.999, so super high standard, so make Wada happy. and the results. So if we just took this test as is, 85% sensitive, 85% specific, and ran through some real-world prevalence, you kind of crash and burn a little bit. I mean, it's okay, but not super useful. Positive predictive value, 66%. Negative predictive value, 73%. It's okay, not great. And most concerningly is that network prevalence, only 50%. So the test result has nothing to do with whether this person is in a high doping network or low doping network. On the other hand, once we use this information, this transverse approach, and use the Bayesian equation to boost the results, the test performs much differently now. Now the positive predictive value, 99.8%. Negative predictive value, 99 or 92.3%, and most importantly, the network prevalence, 77.6%. And so that's, now we're getting the positives, not just randomly, but we're getting the positives in the doping networks. And so that's kind of that key number there. And so that dramatically changes what we're looking at. So if we just took this test and applied in the real world, we couldn't really use it because it kind of classified people sort of, you know, kind of maybe more likely, but not strong enough to do anything with it. And so it approach, you know, if the standard approach, they're poorer predictive values. On the other hand, we've shown that these results with the transverse Bayesian monitoring, we're boosting the accuracy, both positive and predictive, and more importantly, we're getting our positives within the doping network. So now we're getting positives in the middle of the doping network and improving our chances to actually disrupt that doping network. So it's not just randomly knocking some person out of sport. We're now going at the center of those doping networks. And so yes, limitations. It's simulated data, but the importance is on bringing this new idea and showing you that statistically we can do it better, and now we need to do it better in the real world. Thank you for your time.